So, when we're building software, getting the right answer, that's table stakes, right? It has to work. But what happens when your correct code is just painfully slow? Today, we're going to talk about why speed matters just as much as accuracy, and we'll learn the language to describe it. Okay, let's just jump right in with a question. Why would code that's perfectly correct, that gets the right answer every single time, ever be considered useless? Well, think about it from a user's perspective. What if they have to wait and just keep on waiting for that correct answer?
And I'm not talking about a few seconds. Imagine a simple search algorithm, totally correct, but it's sifting through, say, 10 billion items. Even on a really fast computer, you could be looking at a wait time of around 3 hours. 3 hours for one search. All of a sudden, correct doesn't seem like enough, does it?
And that's really the heart of the issue. In the world of software, getting it right is just the starting point. The real challenge, the real goal, is to be right and be fast enough for a human to actually use it. So, how do we even begin to measure this? Do we need a stopwatch for every function? Do we count every CPU cycle? Well, thankfully, no. It turns out we can use something a bit more elegant, the art of approximation. It's all about seeing the big picture of performance without getting totally bogged down in the details. The truth is, trying to calculate the exact running time of a piece of code is a nightmare. It depends on the hardware, the programming language, the compiler. The list goes on. That exact number is a moving target. What we really need is a consistent way to compare two different approaches, a stable yardstick. And that's exactly what approximation gives us. All right, let's get a little more concrete. Imagine we analyze an algorithm, and we figure out that its runtime can be described by this little math function, where n represents the size of the input. So if we're sorting a list, n is the number of items in that list. Now here's where it gets interesting. What happens when n gets really, really big, like millions or billions? Well, that n squared term, it just explodes. It grows so much faster than the other parts that they basically become irrelevant. The 2n and the 3, they're like tiny little houses next to a massive skyscraper. All you can see is the skyscraper, the 3n squared term. It completely dominates the equation. So what do? We simplify. We ignore the smaller terms and even the constant in front. We just focus on the part that's driving the growth. We cut through the noise to get to the heart of the matter. We're not asking, how many seconds does this take? We're asking, what is the character of this algorithm? How does it scale when we throw more data at it? And in this case, the character is n squared. Now, this idea of focusing on the most dominant term, it's not just some random trick. It's actually a formal system, a language that engineers and computer scientists use to talk about efficiency. And that language is called Big O notation. So that n squared we just isolated, in this new language, we'd give it a nickname. We'd say this algorithm is O of n squared, which you'd read out loud as Big O of n squared. It's just a simple, standard way to label this kind of performance behavior. Okay, quick warning. This looks like scary math. Don't worry, you really don't need to memorize this formal definition. The core idea is actually pretty simple. All it's saying is that we're looking for a ceiling. We're saying our algorithm's runtime, which is f of n, will never ever grow faster than some simpler function g of n once our input n gets big enough. It establishes an upper bound. Let's just translate that into plain English. Big O gives you a guarantee. It's like saying, hey, no matter how huge your data gets, I promise you the runtime won't get worse, won't grow faster than this particular rate. It's our worst case scenario for growth. And here's what that looks like in practice. If you have a function like 8n plus 5, the n term is the driver, so we just call it O of n. Same for 2n plus 10. It's still O of n. Now look at the bottom, 10n squared plus 4n plus 2. The n squared is the skyscraper there, right? So we classify it as O(n) squared. We're just plucking out the most significant term and using it as a label. Okay, now that we have this language, we can start to categorize things. Let's take a look at the most common types of growth you'll run into. And you're about to see very clearly that not all algorithms are created equal. So here they are, the usual suspects, generally ordered from best at the top to worst at the bottom. Up top, O of 1, or constant time, is the absolute holy grail. It's incredibly fast. And way down at the bottom, you've got O of 2 to the n, exponential time, which becomes unusably slow almost immediately. And you know what? This graph says it all. This is the whole story right here. Look at those green and blue lines at the bottom. They're almost flat. That's your O log n and ON. They scale beautifully. Even with huge amounts of data, they stay manageable. Now, look at the red and purple lines just shooting off the chart. That's your quadratic and exponential growth. They become impossible to work with for anything but the tiniest inputs. That massive gap between the curves, that's everything. So let's just put the two extremes side by side. On the one hand, you have constant time, O1. This means your algorithm takes the same amount of time whether you give it 10 items or 10 billion items. It's amazing. On the other hand, you've got exponential time, O2n. With this one, the runtime literally doubles every time you add just one single item. The difference is just staggering.
Okay, so why have we gone through all this theory? Why does this actually matter? Because it's what lets us make smarter choices, way before we're committed to a particular solution. Here's the most important takeaway. Big O is a predictive tool. It gives us a shared high-level language to compare different ways of solving a problem on paper before we ever write a line of code. It helps us see which path will scale gracefully and which one is going to lead to a disaster. And that brings us right back to our starting point. An algorithm must be correct, yes, but that's just the minimum requirement. To actually be useful in the real world, it absolutely has to be efficient, too. Understanding Big O is how we avoid that 3-hour search we talked about. It's how we recognize that a linear search, which is O of n, is just the wrong tool for that job. It empowers us to find a better algorithm, maybe one that's O of log n, and turn that 3-hour nightmare into a millisecond blink. And that leaves us with one final thought to chew on. Often, the absolute fastest algorithm is also the most complicated to write and to maintain. So the real art of software engineering isn't just about picking the fastest option. It's about that trade-off. How do you balance the need for raw performance with the very real-world complexity of building and supporting your code?